Hello friends, welcome to the mathematical room. I am the caretaker. So as we have seen in the previous video, the parts of it, the rules of calculus, if we apply them blindly, then that can lead to some serious nonsense, some serious nonsensical results which are useless. So clearly we need a deeper study of calculus. So in this series of videos on real analysis, we are going to review what we already have learned in calculus, but much more rigorously, with as much rigor as possible. So we start at the very beginning. We start with the natural numbers. We already know the natural numbers very well, but now we will be focused mainly on the why aspect, not how to do the calculation, but why a certain calculation or a certain formula is true. That we are going to see. So, for example, we already know one thing from, not even from calculus, a simple thing about numbers. That is the distributive law, AB plus AC. We know this and we have used this so many times that it seems natural, it will always be true. But someone may ask why? Why is it true? And is it really always true? So far, anytime we have used it, it has turned out to be true. Say for example, if I take 2 times 3 plus 5 and if I do the calculation, then it becomes 2 times 8 and that gives me 16. On the other hand, if I have 2 times 3 plus 2 times 5, if I separately do this calculation, then that gives me 6 plus 10, that is also 16. So in this case the formula is true. But of course you cannot consider every possible case separately and show that the formula it continues to be true. Okay, that is not mathematics, that is science. In mathematics you have to prove something in general and then only you can say that this always holds. So that part we have to investigate. Why? Okay. Now, so what we are going to do, we will first of all try to define the system of natural numbers. Try to locate or identify the problems that we encounter in trying to define that system and try to rectify the problems as we go. Now, once we construct the system of natural numbers, you already know from our discussion on knife set theory that by this symbol we mean the set of natural numbers, but here along with the set, by this symbol I mean the system of natural numbers. Now the set is different from system in that the system not only has the set but the two operations of addition and multiplication along with that. So actually I should have written like this, but since the operations are understood, so I simplify the symbol, the notation, and write the system simply as n. Now once we have constructed this system, once we have proved the laws like this that we already know, okay, or we think we know, then we are going to use the system of natural numbers to construct the system of integers. Then from that we will construct the system of rational numbers and then ultimately the system of real numbers. Okay, so we have to get to this, then only we can start analysis or we can start doing calculus. In fact, we will at one point need the system of complex numbers also, but this will not come until we get to section 15.6. By the way, this is second chapter, so section 2.1 it will come. So we will get to section 15.6. There only we will construct the system of complex numbers, primarily for one reason. Although complex numbers are not included in real analysis, but they prove useful in studying trigonometric functions. Studying means constructing trigonometric functions. That we will do, but we have a long way to go before that comes. So this is what we plan to do. This part we will do first of all, and it will take quite some time to construct the system of real numbers and prove all the known properties about it. So we will do this. Okay, now we come to the question of how to actually define the system of natural numbers. How do we define the natural numbers? Now this question may seem very easy, but actually is quite difficult to answer. One difficulty is that we have become accustomed to the system of natural numbers so much that many of these its laws that we already use or we have been using since our childhood, they have become embedded in our brain that it's difficult to let go of them and start from scratch as if you don't know about the system of natural numbers. So what we will now do is we will have to forget whatever we know about them and start afresh. Now, this may actually be difficult. It may sound amusing. Forget whatever you know about the natural numbers. Okay. But that is okay for you. But in your subconscious, those rules are already there. So you may inadvertently end up using some rules. So we have to be careful that we don't use any prior knowledge of n. We have to build and construct everything, prove everything from scratch, and then only after we have proved the thing, we can use it. So that approach we are going to take here. And one more thing is that we are also going to forget that we know anything about the decimal system. Decimal system is very familiar, and it is the system that we use to write numbers. For example, if I write 1, 2, 3, 123, then that really means this: 1 times 10 square plus 2 times 10 to the power 1 plus 3 times 10 to the power 0. This is the units place digit, this is the tens place digit, and this is the hundreds place digit. Okay. In decimal system, the base is 10 and there are 10 characters or 10 symbols. These are the 10 symbols from 0 to 9. We can use these symbols to write a number in decimal system. This is the decimal representation of the number 123. There are other number systems also. In fact, you may already know about them. For example, binary, octal, hexadecimal. In binary system, the base is 2 and the characters are, there are two characters, 0 and 1. So anything you write in binary, in fact if you write 123 in binary, the characters involved will only be 0 and 1. So do you see one thing? The actual entity 123, let me call that A, that stays the same, and these are different representations of that same number. It's like saying something, a sentence in English or in some other language. The meaning of the sentence or the sentence itself stays the same. Its meaning does not change, only the language in which we are saying the sentence changes. So number systems are like the number systems means they are representation. These systems which are used to represent or write the numbers, they can change. So naturally, decimal number system or decimal system, actually I should not say number system, decimal system is not something fundamental to numbers. It's just a way of presenting or writing the numbers. So we will also discard any knowledge. Discard means we will set aside any knowledge that we have about decimal system. And in fact, if you think decimal system is very natural simply because we have been using it for so long, let me show you some questions which will again show that decimal system is not it's not that natural and it's not that easy also. It seems easy because we have used it. There are some questions. For example, let me take this number itself. If I put a 0 in front of it, then the value of this does not change. It stays 123. These two are equal. But if I put a 0 on the right hand side, then the value changes. Why? Of course, this question is somewhat easy to answer. You can use this type of expression to answer this. Okay. Now, but there are some other more difficult questions. One question is, if you look at this number 0.99999, the nines go on and on without any end. This number actually is equal to 1. Why? And by the way, the meaning of 123 is this. What is the meaning of this? What do we mean by this number? What is its definition? So to simply say what it is, let alone showing that this is equal to 1, to just simply say what this is, we need a knowledge of infinite series. So decimal system is not very easy. In fact, some of its rules, like for example, rules for adding and multiplying numbers, they quickly become very messy. So we will not use decimal system. In fact, we will not use decimal system other than the task of writing numbers like this. I mean, we will just, instead of devising some symbol for 123, say we will write 123 in this form only, but we will use decimal system till that only. We will not use any laws of like longhand addition or multiplication laws, carry over 1, add to the next digit. Those things we will not use any of them. In fact, mathematics is not dependent on these systems of representing the objects of mathematics. It's independent of these things. We will develop mathematics without these things. Okay, so we forget the natural numbers and their properties, and also we forget the decimal system. Okay, so this is what first we let's just leave them. We don't know anything, and now we will start. So now we come to the question: how do we define the system of natural numbers? So since we don't know anything, we have to start from scratch. But exactly how? So that we have to figure out. So this is section 2.1. Okay. Now one more thing that I have to say at this point. Okay, let me just first of all start, and then I will say the name is the Peano axioms. Okay, so we are going to define natural numbers using some rules known as Peano axioms. They were first laid out by this mathematician. Yeah, let me just write the dates in which, the time period in which he lived. Giuseppe Peano. Now, these Peano axioms are just one way of defining the natural numbers. This is not the only way. In fact, at one point, we will define the natural numbers in a slightly different way, in one exercise, using cardinality of sets. Now, from our study of knife set theory, we have come across cardinality of sets. A cardinality of a finite set is the number of elements in that set. That idea we will use to define natural numbers in a slightly different way, but it will come later. In fact, we will see that approach in section 3.6. So we have some time for that. Okay, now let us start with the definition. Definition 2.1.1. Okay, so what I wanted to say is that the numbering of these items. 2.1 of course denotes that the fact that it belongs to section 2.1. Now this last number 1, that means this is the first item of this section. Now after definition 2.1.1, I will have a remark. Okay, and that remark will be numbered like this. Remark 2.1.2. It does not mean it's the second remark. It just means it's the second item in the section 2.1. So definition is the first item, remark is the second item. So that way we are going to number the items. And we need this numbering because it will help us refer to these things later when we need them. So for example, I am able to say that we are in an exercise in section 3.6. We will look at another way of defining the natural numbers. So that type of reference, for such references we need this numbering. Now this definition is informal. I will say what informal really means in this context. So let's look at the definition. Let me write from here. So in this definition we are going to try to define the system of natural numbers, or rather a natural number. A natural number is any element of the set which is obtained by starting with 0 and counting forward indefinitely. Okay, so let's now see what this definition says. It says that a natural number is an element of this set. Okay, and the set, what is the set? The set which is obtained by starting with 0 and counting forward indefinitely, 0, 1, 2, 3, 4, like that. Why is this definition informal? This definition is informal because we have used the word set and the word element. Why? We have seen knife set theory, but you remember I have said forget everything about the system of natural numbers, also the decimal system. Forget everything about set theory also. At this point, we don't know anything. Okay, we are not going to assume that we know about sets. That's why this is informal. So what we will do in the course of constructing these number systems, at proper places, we will insert those axiomatic set theory and functions. So those things we will learn as we go along. Okay, so for us sets have not been introduced properly still. So that's why this is informal. It's in the sense of a discussion rather. It's a tentative definition. It's not actual definition. And so that is just one problem with this definition. But there are more serious problems. This definition is not a definition at all. You see, it has vague terms. For example, starting with 0 and counting forward indefinitely. What do I mean by this? It's not mathematical. It's not mathematically precise. I have to say exactly what I mean by starting with 0 and counting forward indefinitely. Okay, that is one difficulty. The second difficulty is that this definition does not say anything about how to add, multiply, or find exponents, or let me write it like this. This definition actually does not tell me anything about the operations that are involved in that are there in the system of natural numbers. How do we define addition, multiplication, and let me write it here, exponentiation. Exponentiation is also there. For example, you can ask what is 2q. What is we see whenever we say something like this, what is 2q? We ask, immediately people will answer 8. No, that is okay. But what is the meaning of 2q? What is the, how do you define the meaning of 2q? So in general, someone may ask what is n to the power m, where n and m are natural numbers. So that sort of thing we are asking. Now we can see, so this definition has actually led us to nowhere. It has shown that the simple way of just saying vaguely, this is the set of natural numbers. A natural number is an element of this set. And how do we get this set? By starting from 0 and counting forward indefinitely. This is nothing. We still have not managed to define the natural numbers, but additionally, we also don't know how to define addition, multiplication, and exponentiation, because these are also part of the system of natural numbers. Not just the set, but the operations also. So let us try to think of a way of answering this second part. What about the operations? In trying to answer this question of how to define the operations, actually it's uh, better to, what should I say? It's convenient to start with exponentiation first. So you will realize why. Exponentiation is nothing but repeated multiplication. For example, if I take that itself, 2q, that number, then that is actually nothing but 2 times 2 times 2. So exponentiation is repeated multiplication. So that means if I know multiplication, I will know exponentiation. So defining exponentiation now becomes a matter of defining multiplication. Okay. Now we come to multiplication. Multiplication is nothing but repeated addition, which we already know. In fact, that's how we, first of all, we are introduced to multiplication. For example, if I multiply 3 with 5, that just simply means adding 5 3 times. So the question of defining multiplication is now the question of defining addition, because if I know addition, then using addition I can define multiplication. So you see that the things are being, already the complexity is being reduced. Exponentiation needs multiplication, multiplication needs addition. So now I can get my job done with addition. But addition is in fact is also not the most basic operation. Addition is the process of repeated incrementation. Now, what is incrementation? It's even more basic than addition. Let's see what that is. incrementation is actually nothing but finding the next element. For us, next means towards the right, of course. So say we want to find 5 plus 3. Okay. Now that actually means what symbol should I use? Okay, let me just first of all use arrows. I find the number next to 5. Let me denote that by this symbol. Okay. The number next to 5 is what? Next means what comes after 5? 6. The number next to 6 is what? 7. The number next to 7 is 8. So these are the incrementation. Every time I increment something, I am actually, you see, we will be tempted to say I am adding 1, but I cannot use the word adding 1 here because I am defining addition in terms of something else. So I cannot use addition. I will say the next one. So that's why it's a different operation. It's even more basic. You locate a number, then find the next one. So that is incrementation. The increment of 5 is 6, increment of 6 is 7, increment of 7 is 8. So that is the answer. So this is in terms of addition I have written. If I write in terms of this operation, this will look like this. 5 plus 3 is actually increment of 5, increment of that, increment of that. So I apply incrementation 3 times. Okay, so that's why addition is repeated incrementation. Now this operation of increments or incrementation is something that does not seem to be reducible to even something simpler. In fact, we don't need more simplicity. So what we will do, we will start with 0 and then use the incrementation operation to generate the other numbers. Okay, so that's how we are going to proceed to define the natural numbers. So this discussion has led us to this point. Oh, and one more thing. Okay. Now this symbol I have only used these arrows to explain the thing, but we will need an actual notation. The increment of n is a natural number, will be denoted by n plus plus. This is just a notation. This simply means that it's the next one. So in this notation, this looks like this. Somewhat cumbersome, but we have to tolerate this much for the sake of defining the system. Okay, it looks awful, but we will get to neater notation when we develop all the things. So it seems that to define the system of natural numbers, we start with basic concepts. The number 0 and the incrementation operation. So to define the system of natural numbers, we will use these two things, the number 0 and the incrementation operation. And the discussion that we have had here, it seems to suggest that the natural numbers are these: 0, then the number next to 0, then the number next to that, and so on. The number next to that. This notation will quickly become unwieldy. Right? So because this notation becomes cumbersome and quickly is unmanageable, so we make another definition. Oh, but before that definition I have to, I forgot about that, sorry. There is a remark. So this is the second item of this section. This remark says, in some treatments, of the natural numbers,